Let's talk about singular value decomposition. A symmetric matrix A has the orthonormal diagonalization P, D, P inverse. What do we mean by orthonormal diagonalization? We know what it means for an n by n matrix A to be diagonalizable. It means we can express A in the form A equals P, D, P inverse, where P is an invertible matrix and D is a diagonal matrix. We know what it means for an n by n matrix A to be orthonormally diagonalizable. It means A is diagonalizable with P an orthonormal matrix. That is, the columns of P are unit vectors that are orthogonal to each other. In other words, we can express A in the form A equals P, D, P inverse, where P is an orthonormal matrix and D is a diagonal matrix. Some books say P is an orthogonal matrix and call this an orthogonal diagonalization, which is confusing because the columns of P are not merely orthogonal. They're not just orthogonal to each other, but orthonormal. That is, they're orthogonal to each other and they're unit vectors. So even though most books would say P is an orthogonal matrix, this is an orthogonal diagonalization, I'm going to say P is an orthonormal matrix and this is an orthonormal diagonalization. Again, a symmetric matrix A has the orthonormal diagonalization A equals P, D, P inverse. If A is not symmetric, we cannot do this. We can, however, obtain a similar factorization for any m by n matrix A. This enables us, for example, to obtain a more accurate answer for an equation like AX equals B with less round-off error. Let A be an m by n matrix. Then A transpose A is a symmetric n by n matrix. How do we know? A transpose A transpose, again, use the law of transposes. This is going to be the same thing as A transpose times A transpose transpose. Again, because one of the rules of transpose is that we reverse the order of the elements when we take the transpose. Okay, but A transpose transpose is just A. So notice this. A transpose is A transpose A. So if a matrix is its own transpose, that means it's symmetric. Because A transpose A is symmetric, it can be orthonormally diagonalized. That is, A transpose A can be expressed in the form P, D, P inverse, where P is an invertible matrix and D is a diagonal matrix. The entries along the diagonal of D are the eigenvalues of A transpose A, and the columns of P are the corresponding eigenvectors of A transpose A. Recall that orthonormally diagonalized means the matrix P is orthonormal. The column vectors form an orthonormal set. That is, they're orthogonal to each other and they are unit vectors. They're also a basis. How do we know? P is an invertible n by n matrix, so the columns form a basis of Rn. That's just one of the statements in the invertible matrix theorem, that monster theorem that had lots of equivalent statements. Thus, the columns of P are the eigenvectors of A transpose A, and they form an orthonormal basis of Rn. Suppose the corresponding eigenvalues of A transpose A are lambda 1, lambda 2, blah, 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 lambda sub n. It turns out that all of the eigenvalues are non-negative. Here's how we know. Notice that the length of AVI squared, that's just going to be AVI transpose times AVI. We've seen before when you multiply a matrix and its transpose, you just get the length squared. And let's apply the law of transposes. That's going to be VI transpose A transpose times AVI, which can be rewritten as VI transpose lambda I VI, because VI is an eigenvector for A transpose A. So A transpose A is just going to be, times VI, is going to be lambda I VI. Lambda is a constant, so we can pull it to the outside. We have lambda I times VI transpose VI, but VI transpose VI, that's just going to be the length of VI squared, because when you take the transpose of a vector by itself, you get the length squared. And lambda I, length of VI squared, that's just lambda I, because VI is a unit vector. Okay, so its length is going to be 1. Thus, they are non-negative. Again, the eigenvalues are non-negative because notice lambda I equals something squared. So it must be either 0 or a positive number. We will put them in decreasing order so that lambda 1 is greater than or equal to lambda 2 is greater than or equal to blah, 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 is greater than or equal to lambda n, which is greater than or equal to 0. The singular values of A are the square roots of the eigenvalues of A transpose A. They are also equal to the length of AVI, the lengths of the vectors AVI. We use the symbol sigma I equals square root of lambda I to represent the singular values. Let A be an m by n matrix with rank R. then A has singular value decomposition, SVD. A equals U sigma V transpose. Where? Okay, let's look at what U, sigma, and V are. First, what's V? The columns of the n by n matrix V are the unit eigenvectors of A transpose A, corresponding to the ordered eigenvalues, lambda 1, lambda 2, blah, 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 lambda sub n. What's sigma? The first entries along the diagonal of the n by n matrix sigma are the non-zero eigenvalues of A. These are sigma 1 equals square root lambda 1, sigma 2 equals square root lambda 2, dot, 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 sigma r equals square root of lambda r. These are the square roots of the non-zero ordered eigenvalues of A transpose A. There will be r of these entries. R, again, is the rank of A. And the other elements of sigma are zeros. What's U? The first r columns of the m by n matrix U are U sub I equals AVI over length of AVI. In other words, AVI over the square root of lambda I. We saw that's equal to the square root of lambda I. That's AVI over sigma I, and they form an orthonormal basis for the column space of A. The other columns of U are obtained by extending U1, U2, blah, 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 U sub R again was the rank of A, to an orthonormal basis, U1, U2, blah, 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 U sub M of Rm. A, again, was an m by n matrix, so M is the number of rows of A. And again, R was the rank of A. The matrices U and V are not necessarily unique. Okay, just crying out, just dying for an example. Construct a singular value decomposition of the 2 by 3 matrix A equals 4, 11, 14, 8, 7, negative 2. Okay, let's first find V. Recall that the columns of the n by n matrix V are the unit eigenvectors of A transpose A, corresponding to the ordered eigenvalues, lambda 1, lambda 2, blah, 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 lambda sub n. Okay, we're going to do this the quick and dirty way. We find the eigenvalues and eigenvectors of A transpose A by using Mathematica or Wolfram Alpha or some other similar program. Okay, so if you use your calculator or Wolfram Alpha to find A transpose A, this is what you end up with. And then if you use Mathematica or some similar program to find the eigenvalues, you get 360, 90, and 0, and the corresponding eigenvectors are these. 1, 2, 2, negative 2, negative 1, 2, 2, negative 1, or 2, negative 2, 1. Okay, so these are the corresponding eigenvectors. We want unit eigenvectors. Again, each of these vectors has length 3. So you divide the length of these vectors by 3, and you get these vectors. These are unit eigenvectors, v1, v2, and v3. Thus, V is going to be the matrix consisting of these unit eigenvectors. Those are going to be the columns of the matrix V. Let's find sigma. Recall that the first entries along the diagonal of the m by n matrix sigma are the non-zero singular values of A. They are sigma 1 equals square root lambda 1, sigma 2 equals square root lambda 2, blah, blah, blah. Sigma r equals square root of lambda r, the square roots of the non-zero ordered eigenvalues of A transpose A. There will be r of these entries. Again, r is the rank of A. The other elements of sigma are zeros. These were the eigenvalues we saw a moment ago, 360, 90, 0. So the non-zero eigenvalues, well, again, we just take the square roots of these eigenvalues. Square root 360, square root 90, that makes up the diagonal of this matrix, and everything else is 0. We can simplify square root of 360 and square root of 90 in this way, and so we get sigma equals 6 root 10, 0, 0, 0, 3 root 10, 0. Okay, let's find U. First r columns of the m by n matrix U are ui equals avi over length of avi. That is avi over the square root of lambda I. We saw that the square root of lambda I is length of avi. Or in other words, avi over sigma I, and they form an orthonormal basis for the column space of A. In our example, R is 2, R is the rank of A, and A is an m by n matrix, 2 by 3 matrix, so we can see that M is 2. Again, M is the number of rows in the matrix A, M is 2. The above formula gives us the first 2 columns of the 2 by 2 matrix U. We need M columns. Okay, so this gives us R columns, and we need M columns. Okay, so mercifully, R and M are the same number here, so we don't need to follow this other prescription. The other columns of U are obtained by blah, blah. We don't need that, because we've already got what we need. We have everything we need. So U1 is going to be AV1 over length of AV1, AV1 over sigma 1. Sigma 1 was 6 root 10. This is A. This is V1. Multiply them together. We get this. And that's going to be 1 over 6 root 10, 18 over 6. In other words, it's 3 over root 10, 1 over root 10. U2 is AV2 over length of AV2. It's AV2 over sigma 2. This is sigma 2, 3 root 10. This is A. This is V2. Multiply A and V2 together, you get this, which simplifies to 3, negative 9. And then the whole thing simplifies to 1 over root 10, negative 3 over root 10. We don't need any other columns because, again, R is the same as M in this case. So this is our matrix U. 3 over root 10, 1 over root 10, 1 over root 10, negative 3 over root 10. Note that this is indeed an orthonormal basis for the column space of A, which is R2. Let's check our answer. Does A really equal U sigma V transpose? This is U. This is sigma. This is the transpose of V. It's not V. It's the transpose of V. When you multiply it together, oh my goodness, thankfully, we got the right answer, A. Okay, let's do another example. Construct a singular value decomposition of the 3 by 2 matrix A equals 1, negative 1, negative 2, 2, 2, negative 2. So let's first find V. Recall that the columns of the n by n matrix V are the unit eigenvectors of A transpose A, corresponding to the ordered eigenvalues, lambda 1, lambda 2, blah, 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 lambda sub n. We find the eigenvalues and eigenvectors of A transpose A by using Mathematica or Wolfram Alpha or some similar program. This is A transpose A, and when you use software to find the eigenvalues, the eigenvalues of this matrix are 18 and 0, and the corresponding eigenvectors are these. That's the eigenvector. 1, negative 1 is the eigenvector for 18, and 1, 1 is the eigenvector for 0. Now, other software may tell you that the first one is negative 1, 1, and not 1, negative 1, but that's okay. That's just a scalar multiple of the one we have. And any non-zero scalar multiple of an eigenvector is going to be an eigenvector. So don't be spooked if some other software gives you this answer instead of this answer. Okay, these are the corresponding eigenvectors. Oh, but we want unit eigenvectors, so we need to divide by the length. So when we divide each of these by the length, they both have length square root 2, this is what we end up with. 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2. Those are going to make up the columns of our matrix V. Let's find sigma. The first entries along the diagonal of the m by n matrix sigma are the non-zero singular values of A. They're sigma 1 equals square root lambda 1, sigma 2 equals square root lambda 2, blah, blah, blah. Sigma r equals square root lambda r. The square roots of the non-zero ordered eigenvalues of A transpose A. There will be r of these entries. R again is the rank of A. The other elements of sigma are zeros. So the eigenvalues we had were 18 and 0. And so the non-zero eigenvalues make up the diagonal. Well, there's only one, so we start the diagonal with square root 18, and then we just run out of steam. There are no other non-zero eigenvalues, so everything else along the diagonal, in fact, everything else in the whole matrix is just going to be 0. Square root of 18 is 3 root 2, so we can simplify sigma to look like this. Let's find U. The first R columns of the m by n matrix U are U sub I equals AVI over length of AVI, which is AVI over square root lambda I, which is AVI over sigma I, and they form an orthonormal basis for the column space of A. In our example, R equals 1, and A is an m by n matrix. That's a 3 by 2 matrix. So m, the number of rows of A, that's 3. The above formula gives us the first column. Again, it just gives us R equals 1 column of the 3 by matrix U. Okay, so we're going to have to do some fancy stuff. We're going to have to use that other technique to find the other columns, because the technique we're about to use gives us 1 column, and we need all 3 columns of the matrix U. Okay, so here's our first column, AVI over length of AVI. That's AVI over sigma 1. Sigma 1 was 3 root 2. This is A. This is V1. Multiply them together, we get this. So 1 over 3 root 2 times this vector turns out to be this, which simplifies to 1/3, negative 2/3, 2/3. So that's our first column of U. That's U1. So we get this one column. The other columns of the 3 by 3 matrix U are obtained by extending U1 to an orthonormal basis, U1, U2, U3 of R3. How do we do this? We throw in standard unit vectors and then prune the ones that we don't need. Okay, so we've got this vector, 1/3, -2/3, 2/3, and then we throw in these other unit vectors. Okay, this spans R3, but it is too big to be a basis for R3. R3 is three-dimensional. It should have just 3 vectors. So we apply reduced row echelon form, ref, to the matrix. And when you do that, this is what you get. So the first 3 columns are the pivot columns. And that implies that a basis for the above matrix, and thus for R, is going to be these 3 columns in the original matrix. Okay, so not the 3 columns of this matrix, the ref matrix, but the first 3 columns of this matrix. Okay, so that'll be our basis for R3. So we've got 1/3, -2/3, 2/3, 1, 0, 0, 0, 1, 0. Awesome. Is this an orthonormal basis? No, it's not an orthonormal basis. Let's apply the Gram-Schmidt orthogonalization process to get an orthonormal basis. Recall that this is how it goes. Okay, so I'm going to put this slide up here, and we'll just go through this step by step for each of them. Step 1, 2, 2 prime, 3, 3 prime, etc. Okay, step 1. So again, here's what we do with step 1. We let V1 equal X1. That is, in other words, 1/3, -2/3, 2/3. W1 is going to be the span of X1. Here's what step 2 is. Step 2, we let V2 equal X2 minus X2 dot V1 over length of V1 squared times V1. That's, in other words, X2 minus the projection of X2 onto W1, in case you were wondering. So we have V2 equals X2, that's our X2, minus X2 dot V1 all over length of V1 squared times V1. So when you take the dot product, you end up with 1/3. The length of the vector, that just turns out to be 1. And then we still have this vector here. Multiply it all out, you get 1, 0, 0 plus -9, 2/9, -2/9, and that simplifies to 8/9, 2/9, -2/9. Recall step 2 prime, multiply V2 by a constant to simplify later calculations. Yeah, because we don't need to deal with 8, 2, 2, okay? You know, we don't need to deal with 8/9, 2/9, -2/9. We can just multiply it by 9. May as well. Just makes it easier to calculate. So we end up with 8, 2, -2. It doesn't matter what the length of the vector is. You know, we just need a vector in this direction. And step 3, let V3 equal this hairy expression. Okay, X3 minus X3 dot V1 over length of V1 squared times V1 minus X3 dot V2 over length of V2 squared times V2. You can also think of that as X3 minus the projection of X3 into W2, but you don't need to know that. That's where W2 is the span of X1, X2. Okay, let's look at step 3. So we let V3 equal X3 minus X3 dot V1 over length of V1 squared times V1 minus X3 dot V2 over length of V2 squared times V2. This is our X3. This is going to be X3 dot V1 over length of V1 squared. That's V1. This is going to be X3 dot V2 over length of V2 squared times V2. So let's do the math. This is the dot product that we have over here. The length of the denominator squared, that's just going to be 1. And then we have this vector out front. Okay, as for the second expression here, the dot product of these two just turns out to be 2. The length of this vector squared is going to be 72, and then we still have 8, 2, -2 there. Let's simplify. This is what we had from the previous slide. So -2/3 over 1. Negative signs cancel. We're just left with 2/3. 2 over 72 is 1/36. Multiply that out, and you end up with this. In other words, when you find a common denominator of 18, this is what you get. All of that simplifies to 0, 9/18, 9/18, which is 0, half, half. Okay, and again, we multiply that by a constant to simplify later calculations. We don't need 0, half, half. We can multiply by 2 and get 0, 1, 1. Who wants fractions? Why deal with fractions? Check. Are the two vectors v1 and v2 orthogonal to v3? Yes, you'll find that their dot products are 0. So an orthogonal basis for R3 is this. But we need an orthonormal basis, so we need to divide each of these vectors by its length. Okay, so this vector was fine. This vector divided by square root of 72, which is its length. This vector divided by square root 2, which is its length. This simplifies a little bit. Square root of 72 is 6 root 2. And so when you grind it out, that's what you end up with. Okay, so this again was what we had from the previous slide. You can simplify it a little bit, okay, and end up with this. That's going to be our vector u1, u2, u3, or our vectors u1, u2, u3. That's u1, u2, u3, so that means our vector, our matrix U is going to look like this. Let's check our answer. Oh my goodness, I hope it's correct. So A should be U, sigma, V transpose. Oh my goodness, yes, it does work out well. I verified this product on the TI. Now Mathematica and Wolfram Alpha can do singular value decomposition. So for example, if you ask them to construct the singular value decomposition of the 3x2 matrix we just saw a moment ago, you can just enter this. Singular value decomposition. Notice how you have to enter a matrix. Okay, use curly brackets for the columns, or I'm sorry, for the rows, and then you enclose all of that with more curly brackets to represent a matrix, and it yields this. Wow, that was quick. Now, we had this. Notice that these two are not the same. Note that the singular value decompositions are different for U and V. These two are not the same. Okay? But that's okay because the singular value decomposition is not necessarily unique.